Hello everyone, welcome to my channel. In the previous lecture we have discussed about mass transfer correlation. Now in this lecture we will discuss mass transfer correlation. We have discussed these equation. Now in this lecture we will discuss the mass transfer to a single particle. Suppose we have a single catalyst particle which is spherical in shape, and suppose there is some fluid which are flowing around the catalyst particle, and suppose this is a fluid which are flowing around the catalyst particle. Fluid is flowing around the catalyst particle. So the mass will transfer from the fluid to the catalyst. The velocity of the fluid is suppose u. The mass so the fluid, this is the fluid, this is the catalyst particle, and suppose there is some hydrodynamic boundary layer around the catalyst particle. So if fluid is flowing around a catalyst particle, then the fluid will form a boundary layer around the catalyst particle. So it will be the hydrodynamic boundary layer. This layer is called this yellow layer is called the hydrodynamic boundary layer. The fluid will form a hydrodynamic boundary layer around the catalyst particle. The thickness of the hydrodynamic boundary layer is theta. This is the thickness of the hydrodynamic boundary layer. So in some cases either the component A will transfer from the surface of catalyst. In some cases the component A will transfer from the flow to the surface of the catalyst. So in some cases the component can be transferred from the fluid to the surface of the catalyst. This is the bulk flow. Concentration of component A in the bulk flow is CAB, and the concentration of component A at the surface of the catalyst is denoted by CAS. We have already discussed this type. So mass transfer to a single particle. This is a single particle, and mass is transferring from the flow to the surface of catalyst. So there are two conditions, there are two limiting cases. In the first case is the diffusion towards the surface, the diffusion from fluid towards the surface of catalyst is very small. In first case the diffusion is very small. So in first case diffusion is slow. Diffusion which are taking place in the hydrodynamic boundary layer is very slow in the first case. So diffusion in this hydrodynamic boundary layer is very small in the first case, and reaction at the surface of the catalyst particle is very high. So this is the first case. Reaction is high. Reaction at the surface of catalyst is very high, very rapid reaction. This is the first case. The second case is opposite. In the second case diffusion is very high. Diffusion through the hydrodynamic boundary layer is very high. Diffusion of component A through hydrodynamic boundary layer is very high. So large diffusion or very rapid diffusion or high diffusion, high or rapid diffusion, and the reaction at the surface of catalyst particle is very slow. So very slow reaction at the surface of catalyst is very slow. So there are two conditions. In the first condition diffusion is very slow in the hydrodynamic boundary layer, and reaction at the surface of catalyst is very rapid. In the second case diffusion is very rapid through the hydrodynamic boundary layer, and reaction at the surface of catalyst is very slow. So we will discuss the first case in which diffusion through the diffusion of component A through this hydrodynamic boundary layer is very slow, and reaction at the surface of catalyst particle is very rapid. So we will discuss this one with the help of example. Now this is example 14-1 in the book of Element of Chemical Reaction Engineering by Fogler. Element of Chemical Reaction Engineering by Fogler, 5th edition. Now this is the example 14-1, rapid reaction on the surface of catalyst. So this is the first case in which reaction at the surface of catalyst is very rapid, but diffusion through the hydrodynamic boundary layer is very small. So the diffusion is very small, but reaction at the surface of catalyst particle is very rapid. So calculate the molar flux WAR of reactant A to a single catalyst pellet 1 cm in diameter. The diameter of the catalyst particle is 1 cm and suspended in large body of liquid B. So reactant is component A and the liquid is component B. The reactant is present in dilute concentration and the reaction is considered to take place instantaneously at the external surface of the fillet surface. So the concentration of component A at the surface of catalyst is 0, approximately 0. Now the bulk concentration of component A is 1 molar and the free stream liquid velocity past the sphere is 0.1 meter per second. So there is a catalyst particle which is present in a large body of liquid. The diameter of the catalyst is given to us. This is the diameter, which is 1 centimeter. The component A, this is the catalyst particle, and there is a this is the liquid which are flowing around the catalyst particle. So the liquid flowing around the catalyst particle and the liquid are forming the hydrodynamic boundary layer around the catalyst particle. So it formed the hydrodynamic boundary layer, this type of hydrodynamic boundary layer around the catalyst particle. Hydrodynamic boundary layer. The concentration of component A at the surface of catalyst is 0 because the reaction is very fast at the surface of catalyst. So the concentration of component A in this place at the surface of catalyst is 0. CAS is 0. It is given to us. Now the velocity of the fluid is 0.1 meter per second. 0.1 meter per second. So this is the velocity of the fluid which are flowing around the catalyst particle. Now the bulk concentration of the reactant A is 1 molar. So the bulk concentration here, this is the bulk flow. This is the bulk region. This is the bulk region. So here concentration of component A is CAB, which is equal to 1 mole per liter, and the free stream velocity around the catalyst is, this is the velocity of the fluid around the catalyst particle which are flowing around the catalyst particle. The kinematic viscosity, which is equal to the viscosity divided by density. So the viscosity of the fluid divided by density of the fluid is equal to kinematic viscosity, and kinematic viscosity of the fluid is 0.5 centistroke. Now 1 centistroke is equal to 10⁻⁻⁶ meter square per second, and the liquid diffusivity of A and B. So the diffusivity of component A in the component B will be equal to, now the diffusivity of component A is, this is the component A which are, and this is the component B, this is the liquid is component B. Now the component A is diffusing from the liquid to the catalyst surface through this hydrodynamic boundary layer. So the diffusivity of component A in the liquid in this component B. So the diffusivity of component A of this component A, suppose this is the component B, this is the liquid around the catalyst particle. So the diffusivity of component A in this component B, this is component B, this one. The hydrodynamic boundary layer thickness is considered to be component B. So the diffusivity of component A in this component B is given to us. It is 10⁻⁻10 meter square per second at 300 Kelvin. So the whole process taking place at 300 Kelvin, constant isothermal condition. Now this is the diagram. This is the catalyst particle. The diameter is given to us 1 centimeter, and this is the hydrodynamic boundary layer around the catalyst particle. This one is the hydrodynamic boundary layer around the catalyst particle. This is the thickness of the hydrodynamic boundary layer. This is given to us, thickness of the hydrodynamic boundary layer. The concentration of component A at the surface of catalyst is denoted by CAS. and the concentration of component A in the bulk flow, this is here bulk flow is present here in this positions. So in this bulk position, the concentration of component A in the bulk position is denoted by CAB or CA. You can also write it CA or CAB. CAB is equal to CA. So you can write either CA or CAB. The B stand for bulk region. So and CA mean concentration of component A in the bulk region. Now we have to determine the radial flux of component A. So the flux of component A, the question is determine the flux of component A in the radial direction of. So the flux of component A in the radial direction, this one. Determine the flux of component A in the radial direction. This is the radial direction. This is the radial direction because we are considering this is the radius of the catalyst particle. So this is the radial direction, and the flux is denoted by WA. Flux of component A in the radial direction is denoted by this. So we have to determine this WAR, flux of component A in the radial direction. Now for dilute solution, we know that for dilute solution, for dilute concentration, the radial flux is equal to, this is for the dilute concentration. So for dilute concentration, suppose this is a catalyst particle and it is present in the fluid. So the dilute, this is the fluid is very dilute, is very dilute. So for dilute case, so this is the hydrodynamic boundary layer, this is the flux. So for dilute case, the flux of component A in the radial direction will be equal to Kc. This is the mass transfer coefficient, this is the concentration of component A in the bulk, and this is the concentration of component A in the at the surface of catalyst. Now this is the first condition. We have already discussed that there are two conditions. One is the diffusion, in one case diffusion is very slow, and in the second case the reaction is very slow. So in this case the reaction is very fast, but diffusion is very slow. So at the surface of catalyst the reaction is very small. So concentration of component A at the surface of catalyst is considered to be 0, because when component A coming to the surface of the catalyst, rapidly it will be converted into component B. So here the concentration of component A will be, and at this place the concentration of component A will be 0, but the concentration of component B will be very high. So the CAS will be 0, which is given in the question. Because reaction is assumed to occur instantaneously on the surface of the catalyst, so this is 0. CAB is given, which is 1 molar. 1 molar is equal to 1 mole per dm cube or 1 mole per liter, because 1 dm cube is equal to 1 liter. 1 liter. Now the mass transfer coefficient for single sphere is calculated from the Froehlich correlation. From this correlation, so this is the correlation is Sherwood number is equal to this one, and we know that Sherwood number is the mass transfer coefficient, diameter of the particle, and diffusivity of component A in the component B. Remember, component A in this case is component A is denoted by A, and liquid water is component B in this case. Now we know that Reynolds number is equal to density of the liquid, diameter of the catalyst particle, and this is the velocity of the liquid which are flowing around the catalyst particle. This is the viscosity of the liquid. Now we know that the density divided by viscosity divided by density is equal to kinematic viscosity. So in place of if we divide this by density, we will get kinematic viscosity, which is this one, and this is the diameter of the particle. The diameter of the particle is given to us 1 centimeter. So 1 centimeter is equal to this one, and this is the velocity of the liquid. The kinematic viscosity value is given to us, this one 0.5 centistroke, and this is equal to in meter square per second. So the Reynolds number is come out to be 2000. Now the Schmidt number, what is Schmidt number? It is the ratio of momentum diffusivity divided by mass diffusivity. Now what is momentum diffusivity? It is equal to kinematic viscosity, and the value of kinematic viscosity is this one. So this is the value of kinematic viscosity. Put it in this place, and the diffusivity of A and B is in the question. It is given to us 10 raised to power minus 10 meter square per second. So the Schmidt number is 5000. Now substitute the value in equation in this equation. So in this equation substitute the value of Reynolds number and Schmidt number in this equation. So Reynolds number is 2000 and the Schmidt number is 5000. So after calculation, the Sherwood number will be 460.7. Now from the Sherwood number we can get the mass transfer coefficient. So we know that the Sherwood number is Kc into diameter of the particle divided by the diffusivity of component A in the B. So Sherwood number is obtained 460, that is 460, and the diffusivity of A and B is given to us 10 raised to power minus 10, and diameter of the particle is 1 centimeter. So you can easily determine the mass transfer coefficient. So the mass transfer coefficient here in this position, the mass transfer coefficient is 4.61 10 raised to power minus 10 meter per second. This is the mass transfer coefficient, and the CAB is value is given, it is 1 molar. So simply put the all value in this equation. WA flux of component A in the R direction is Kc into concentration of A in the bulk flow minus concentration of A at the surface. So concentration of A at the surface is 0 because due to rapid reaction, and concentration of A in the bulk flow is 1 molar. So it is 1 molar, and multiply it with Kc, which is mass transfer coefficient. Now the mass transfer coefficient value is this one. So multiply this value with 1 molar. So you will get the flux of component A in the radial direction, which is this one, this mole per meter square into second. Now the flux at radial direction is equal to the reaction rate at the surface of catalyst. So WAR is equal to minus RS. This rate is also the rate of reaction per unit surface area of catalyst. So this flux is equal to the rate. So once the reactant, this means that this is catalyst, this is hydrodynamic boundary layer, and this is a liquid. So this is component A, this is component A. So it means that once component A reaches, as component A reaches from the hydrodynamic boundary layer to the surface of the catalyst, instantly it will convert it into component B, and the rate of conversion of component A at the surface of catalyst will be equal to the rate of flux of component A which are flowing in this radial direction, which is equal to WAR. So the WAR will be equal to the rate of disappearance of component A at the surface of catalyst. So the rate of disappearance of component A at the surface of catalyst will be equal to this one, and this is also equal to the flux of component A in the radial direction. So this was just example to the one of the cases which we have already discussed. Thank you very much for your attention. If you are new to the channel, please like and subscribe.